Again, my name is Dr. Josh Mackey, coordinating the GreenTalks, and we will have 10 speakers this semester, talking about all sorts of things from design from an environmental perspective, managing water, building things with fungi. That's going to be an interesting one. In a few weeks, we are going to have a talk with birds of prey in the room. It's all okay. Nobody's going to get sued. Today, I'm really happy to be introducing somebody who thinks about the environment at many different levels. Dr. Eugene Cordero, he's a professor here at San Jose State in meteorology. His research is super cool. It has to do with the atmosphere and chemistry. And he's looking at all the scientific indicators of climate change. He's also an expert in teaching storytelling and has started a very solid education program for basically K through 12 kids and teachers on environmental science called the Green Ninja Project. So he's going to talk about a lot of things today. Keep those questions in mind for the question and answer session at the end. And with that, if you could just welcome Dr. Eugene Cordero, please. Is your microphone on?
Now it's green. Oh, that's much better. Well, I learned something already. I hope that you at least learn to push an on button. I'm a professor here in meteorology, and I am excited to be here. And so we're going to talk about climate change today. So here I am. I'm a doctor. Well, maybe not that kind of doctor. But here on campus, actually some people know me as Dr. Burrito. And I know that's a kind of odd and quirky name. And hopefully through today's talk, you'll get to know how I got that name. But I started at Cal State Northridge, and I was actually at one point an engineer. I was a civil engineer, but then I switched over to physics. And I remember taking a public speaking class. You've taken public speaking as well. And I ended up talking about this formula. And this formula actually kind of changed my trajectory in terms of my science. So this says that chlorine plus ozone produces chlorine monoxide plus oxygen. And then that chlorine monoxide, which you've just produced, can react with oxygen to produce chlorine and more oxygen. And this is called a catalytic cycle. And this catalytic cycle, what it actually does is that it takes ozone plus chlorine and it decomposes, it gets rid of the ozone, but reproduces chlorine again. So one chlorine atom can react with 100,000 ozone. It can convert 100,000 ozone molecules. And the scientists, we were scientists at that time, understood this process very well. But what they didn't understand is that this could happen over and over again and cause something that we know as the Antarctic ozone hole. And so this blue area right here are very low ozone values. And this was discovered in 1985 by NASA satellites and some people who live in Antarctica who were doing measurements. And it was a big surprise to everyone that ozone values were declining. And in fact, it was such a surprise that the NASA satellite that was observing ozone had a bug in there. It said if ozone values are lower than a certain amount, the data must be bad, if-then statement. And only then, at one point, some scientists said, oh, wow, there's a lot of bad data over Antarctica in the springtime. And they discovered this ozone hole. So that's a story that many of you already heard about, that the chemicals that were being released from things like Freon or from refrigerants we're actually inadvertently destroying the ozone layer. And those small, in that catalytic cycle that I just showed you, one chlorine molecule destroying a whole bunch of ozone, that was part of the process. So Antarctic ozone hole, potentially really bad thing. And so if you look at measurements of the thickness of the ozone layer, that the ozone layer started off as its normal thickness. And remember that this is what protects the planet from harmful UV radiation. So if we didn't have an ozone layer, we wouldn't be living here. We wouldn't have life on this planet. So the thickness of the ozone layer over the last 30 or 40 years started to decline, and we started to understand why that was. And then the good news is that this is the future. And the quick story is that the scientists discovered this. They told their friends, basically policymakers, who then developed some type of agreement to say, well, let's get rid of those chemicals. Let's produce ozone-friendly chemicals. And we've done that. Something called the Montreal Protocol and later international agreements have said, okay, we're going to phase out these ozone-depleting chemicals. And so this green line that says future, this is the prediction for the next 50 years of how the ozone layer is actually going to recover. So it's a real success story. Now, what if we hadn't listened to the scientists? What if we said, oh, no, that's not really true. How could a really small amount of chemical have an effect on our climate system? Well, we've done some simulations to show how the ozone levels would have changed in the future if we hadn't done anything. This is called the future world that we avoided. So we would have, the amount of ozone in the atmosphere would have gone, down to maybe a third or even a quarter of what it was originally. So what would the world be like in that case, the future world that we've avoided? Well, every day there's something called a UV index, which tells you the strength of the sun, the strength of the UV radiation impacting. This is a day in September. You can see that, in California it's 8 or 10. The maximum, if you look here, it goes from green to kind of magenta. It's basically telling you how fast your skin, a light-skinned person, how fast their skin would burn. So this happens every day. These are kind of normal values. If we look at the future world that we've avoided, the values, instead of 8 or 10, which is kind of getting up towards high and extreme, we could have got up to like 25 or 30. We could have really changed our planet. And by 2050, if we hadn't paid attention to the science behind ozone depletion, if we hadn't taken action in terms of policy, an average person could be sunburned in less than 5 minutes by the year 2050. So imagine what that would be like. It might look like this. Or hopefully not like this. Or maybe it would look a bit like this. So the good news is that that didn't happen. We have taken the steps to do something about our ozone. And ozone depletion was the first thing as a scientist that I worked on when I was a scientist at NASA Goddard. So this leads me to kind of the first thing that I learned, and I'm going to show you a few different things I've learned in terms of being a scientist and studying the atmosphere and climate. Number one is that small things can be important. Small things meaning that the amount of extra chlorine that we put in the atmosphere that destroyed ozone was measured in parts per billion. It's a tiny, tiny fraction of the atmosphere. And yet sometimes tiny fractions of the atmosphere can make a difference. Small things sometimes matter. That's why as scientists and engineers, we study this stuff. I'm going to just do a little experiment here. This is your drink here?
Yeah.
Okay, can I just borrow it as a prop here? Okay, great. So I'm going to take her drink here, and I got a little chemical in my bag here that I'm going to put in there. I hope you don't mind. And I'm just going to it's a tiny, tiny drop, right? I don't know if you ever heard of cyanide. Anyone heard of cyanide? But it won't matter much because it's a tiny amount. Will it affect you at all, you think? Oh, maybe, right? So, okay, I'm not going to do that. But if I put a tiny amount of cyanide in our water, some of us might be concerned, right? So sometimes small things matter. Now, sometimes they don't. But as scientists and engineers, in this case, we really realize that this small additional chemical in the atmosphere, for some reasons, actually produced a big dramatic change on our planet. Now, actually, looking at our planet, this is the surface of this beautiful place we live, but there's a very thin atmosphere here that is where the ozone layer is. And the ozone layer is also measured in parts per billion. It's a tiny fraction of the atmosphere, but it has an important role. So you've all taken physics and your more advanced classes in your engineering. You know that sometimes, small things matter. So that was a learning experience for me. So after I worked at NASA Goddard for a few years, I actually went to Australia, continuing to do research on ozone depletion. But the field started to switch, and we started to look more at climate change. And that's what I'm going to talk to you about for the majority of the day. So the issue of climate change, we can look at how temperatures on the planet have changed over the last 120 years. So here's a record from the year 1880 to the year 1960. The red line is kind of the 5-year running mean of the temperature. And if I was to ask you to describe that, you might say, oh, the temperatures have kind of gone up and down, But then since 1960, there's still some patterns of up and down, but generally it's going up. And what we're looking at here is global average temperature. This comes from land and ocean data. It's heavily scrutinized. This one comes from the NASA Goddard Institute for Space Studies. They're taking weather stations from all over the world, along with ocean buoys, and this doesn't include any satellites. It's all surface data. But generally, you can see that the temperature is rising, and especially if you look at the last few years. 2016 was a record. The previous record was 2015. The previous record was 2014. Over the last 20 years, all the temperatures have been warmer than previously. And is this a big deal? Like it's only 1 degree Celsius here, which is about 2 degrees Fahrenheit. So the last ice age was only about 4 degrees Celsius colder than today. The last ice age had 5,000 feet of ice over New York. The planet was very, very different. So even though you can't tell the difference between one day that's 1 degree Celsius warmer than the other, when the average temperature of the planet is different by 1 degree, we start to notice. If the average temperature of the planet is different by 2 or 3 degrees, it's a really dramatic change. So it is a big deal. In fact, we're seeing it today. So if you look at this kind of classic picture of a giant glacier over Svalbard, Norway in 1918, and if we look at it today, we can see that large amounts of that ice have gone away because of the warmer temperatures. And another example, in northern Alaska in 1922, this giant glacier, and then today, almost all of that glacier is gone. Actually, what I find remarkable about this, and that most people don't notice, is you see that little iceberg there? It has survived over 80 years of warming. I find that remarkable, but no one talks about that. But more seriously, the ice over the Arctic used to be as big as the area within this orange line. And this was a picture or satellite image from NASA from the year 2012. And so in the summertime, actually some people are getting kind of excited because now you can take a boat from Europe over to North America because it's ice-free, or there's a passage here. And we haven't had that in thousands and thousands of years. But it's not just in summer. Here in winter, this is average January Arctic sea ice extent. You can see that from 1980 through to today, when we've had satellite data to measure this, we can see that the amount of ice is declining, not just in the summertime, but in the wintertime as well. And some people are forecasting ice-free summers over the Arctic. Now, why would that matter? Why do we care? Maybe some polar bears will have their habitat altered or changed quite dramatically. But the Arctic actually keeps the planet relatively cool because it's this cold area. And if that changes, and if you take away the white ice and you replace it with dark ocean, you're going to add a lot more heat to our system. It's something called a feedback, and it can lead to even further warming. So, and other changes. Now, closer to home, we are seeing, and we've been able to witness, changes in our climate system or weather and climate-related extremes for many years. So starting in 2012, we had $100 billion in weather-related disasters. And for those of you working in the civil and water areas, your colleagues notice these things because they're happening every single year. So this one, there was a record drought in the Midwest, and then we had Hurricane Sandy or Superstorm Sandy, which caused huge amounts of damage to infrastructure. 2013, we had 7 weather and climate disasters that cost over $1 billion in damage. These are storms, they're flooding events. And just skipping forward to 2016, which is last year, we were kind of at the end of our western and eastern drought, which cost this state a lot of money. But we had this amazing amount of flooding in Texas and Louisiana. And this is in line with the scientific predictions of how climate change is going to proceed. That is, we're going to see warmer extremes. We're going to see warmer temperatures overall. But we're also going to see more extreme weather. And that's because as you warm the planet, you're going to get more evaporation, and then you're going to get more water vapor in the atmosphere. That's going to drive the potential for more storms. But some places are going to be drier because you're going to start to shift the kind of what is normal. And so we see this, Houston flooding, Texas and Louisiana flooding. And then what did we see yesterday here in San Jose? Flooding. And why is that so surprising? Right, because we've been in a drought, record-breaking drought for the last 4 years. And that's totally in line with the types of extremes that we're not just seeing in California, but we're seeing all over the world. So it's not that climate change is off into the future, that we're witnessing that right now. And it is having an effect on our infrastructure. So any of you live in Santa Cruz, you just kind of, know about Highway 17 and about our roads. In fact, some people were saying recently that it's a great time to go into civil engineering. Because, this stuff's going to continue to happen, and these roads need to be rebuilt, and these bridges need to be redesigned, and infrastructure, and that's related to water as well. But actually, I would say that every field of engineering is going to be needed in our today and moving forward in terms of our climate system. So here's a question that I think people like yourselves might ask is, how do we know what's causing? It's very, very clear that our climate's changing. But how do we know what's causing that climate to change? So I'll just tell you a quick story. When you plug in and most of you already know this story, but when you plug in your laptop or your cell phone for electricity, or when you drive your car, or even the foods that you eat, all of those things require energy to manufacture, to produce. And in most of the world, that energy comes from fossil fuels, which ultimately produce carbon emissions. So when you use your electricity, it came from a natural gas plant. When you drive your car, of course, you're burning oil. And when someone had to manufacture your food and transport it and move it around, all of those ultimately produce carbon emissions. And carbon emissions can change the climate. Carbon dioxide is a heat-trapping gas that keeps our planet nice and comfortable. But we've put more of that gas into the atmosphere, and that can cause our planet its temperature to change. So if we look at ice core data from Antarctica, and it's really cool, interesting engineering to take this drill down into thousands of feet of ice. It's kind of like going back into a time machine, and you can take little bubbles from the ice, and you could see how much carbon dioxide was in the atmosphere. And then using some isotopic signatures, you can also determine the temperature. But if we look back in time, we start 400,000 years ago, you can see that the amount of CO2 in the atmosphere was about 275, and then it dropped. And then it went back up, and then it dropped again. And then it went back up, and then it dropped again. And it kind of followed this repeating cycle over the last 400,000 years. It's kind of a complicated reason to explain why it's done that. There were no humans around. This is probably because of orbital variations, the sun, Earth kind of interacting in some way. But we understand pretty well this, But what we also, and I'm not going to show you, but the Earth's temperature also followed fairly similar signals. It got warmer and got colder and warmer and colder. Over the last 100 years, we went through this, and then we've done this. And we actually, from isotopic measurements, we actually know that this extra carbon dioxide in the atmosphere, this is from the burning of fossil fuels, that there's no other source of this. So this is very different today, our current level. And in fact, if you look at measurements from Mauna Loa, this is the top of a volcano, and that is able to measure very clean air, we can see that carbon dioxide levels are very steadily rising. And this for sure is due to the Industrial Revolution. And an increase in population and industrialization in general. Now, this is not the only thing that can change the climate to change. Obviously, in the past, the sun, and if the sun gets stronger or weaker, that can cause our climate to change. And if you have volcanic eruptions, that can cause our climate to change. So how do we know what's been happening over the last 50 years or over the last 50,000 years? So I'm going to share with you, I'm going to share with you one example of how we know that. There's different lines of evidence that scientists use. And the one I'm going to talk to you about today is called radiative forcing. This is like an energy bookkeeping exercise. For example, for you, you keep track of your finances, you have a checkbook or some type of account, money going in and out. We can do the same thing with energy on the planet. We can keep very good track of the energy coming in from the sun, and then what happens to that energy. And we can keep such good track that we can figure out what effect additional greenhouse gases have on the atmosphere or the sun, all these different factors. But there's other lines of evidence too, and I'm not going to talk about them, but I want you to understand that the reason that scientists think that humans are causing our climate to change is not just like intuition or a guess, that it's based on a system of a systematic investigation, just like you would do in terms of engineering, to look at, well, what else could it be? And so we use climate models, or we use fingerprint detection techniques, or we use actual atmospheric measurements to really try to understand the climate system. So I'm going to give you an example of why this is actually complicated. So many of us today drove our cars, or we were in some type of vehicle that was moving us around. So what's this stuff right here, this white stuff? Somebody. Yeah, what is it?
Carbon dioxide, monoxide.
Okay, some of that is correct. Somebody else. I'm not looking in too detail. I mean, what if you were describing it to your friend? What do they see there? Yeah. Okay. Yeah. Smog. Okay. Yeah, like pollution, like junk. Like anyhow, you guys know that if you put your mouth, like if you really inhale deeply around here, right? You don't really want to do that. Right? That's like junky stuff coming. That's exhaust coming out of it. Now, what color is this? Is it light or dark? Yeah, this white stuff is kind of light in color. Sometimes you see dark exhaust coming out too. The majority of it is light. So, and it does have carbon dioxide. You were right about the carbon dioxide. Although, can you see carbon dioxide? Right, it's invisible. How do you know it's invisible? Exhale, right? I think you've done that recently, right? So when you exhale, I'm going to demonstrate for you. What's coming out of my mouth? Carbon dioxide. Can I see it? No. It's actually one reason I think that we haven't regulated carbon dioxide that quickly. It's because you can't see the stuff. With that stuff, you can see, now we have tailpipe emission controls, and we have all this. That's not completely true, but you can't see carbon dioxide. So what you're seeing here are aerosols. They're little particles, smoke, soot, that are actually visible. And it turns out that ironically, these chemicals, because they're light in color, actually cool the climate. Because sunlight hits them and bounces off and doesn't warm the planet. So there's actually two things happening right now. One is the planet's warming because carbon dioxide is coming out, which we can't see, but we know it is. You could take an instrument and you'd see that instrument you'd see the CO2. But the second thing that's happening is this is cooling the planet. This stuff that we don't want to breathe is actually cooling. That's what we call air pollution. So now my question to you is, which one wins out? The warming due to carbon dioxide or the cooling due to aerosols? Somebody. Warming. Why do you say warming? Can one person, just one person raise your hand, I'll call on you. Yeah.
Past 50 years temperature.
Okay, you're using the, like what's happened to the temperature. It must be winning. I'm just talking about this one car. Yeah.
The smoke will dissipate and the color goes away, but the atoms are still present.
Anybody believe him? That's a reasonable hypothesis, but we'd really have to test this. I think you're basically talking from your gut. Like, that's what your instinct is saying. But to really answer this question, we'd have to do some measurements, right? We'd have to really test this, because there is a possibility that this thing's winning out, that this spreads and then cools, and then the warming isn't that much. It's all about quantity. So as good scientists and engineers, we would set up some tests to really study this before we'd know. So I wouldn't expect actually anyone in this room to know the answer to that question, because it's quite possible that the cooling could overwhelm the warming. So, of course, we've done this type of analysis, and that looks at aerosols and CO2 emissions. So I'm going to show you this. This is kind of a crazy chart, but actually if you understand this chart, potentially you could make a lot of money. And I'm going to explain why you can make a lot of money using this chart. But this is called radiative forcing, and anything that's positive, like it has a positive value, is going to warm the planet. Anything that has a negative value is going to cool the planet. And we're going to look at all the different things that are affecting our climate system that come from humans. We'll compare it also with the sun. So here's extra carbon dioxide in the atmosphere, and these are other heat-trapping gases. And these are causing the planet to warm because they're in the positive direction. This is ozone, and it turns out that it's a little confusing, but ozone's also a greenhouse gas. But in general, this is smog, and that's causing the planet to warm. That smog, that chemical ozone is actually invisible. There's extra water vapor in the atmosphere. We're cutting down, we're deforesting some regions in the tropics, and that's actually causing the planet to cool. And then here are the aerosols I just mentioned to you. These are coming primarily from factories and automobiles, and these are causing the planet to cool. So you can see the warming due to carbon dioxide and the cooling due to aerosols. And you actually see the uncertainty bars, and since you're engineers, you know about these things. So, we don't have direct measurements all the time everywhere in the world, so there's some uncertainty. This is the airplanes that are flying high up and producing clouds. So really try to go into detail about things. Here's the sun. The sun's actually been getting a little stronger over the last 150 years. Not really relevant compared to all the human factors. So if someone says, it's the sun's affecting climate change, not us, well, at least according to our measurements, that's not true. But when you add these all up, all the human impacts, the net forcing is positive. So then going back to what you said, we see the planet's temperature warming, that's in line with this, but also when we do detailed calculations, we see that the human effect is warming our planet. There are cooling factors, we're not discounting that, but when you add them all up, the net effect is warming. The other thing is that these cooling factors like aerosols, we're actually good at getting rid of those because we're good at putting scrubbers on factories and good at making our cars cleaner, but we're not so good at getting the cars to use less fuel. So predictions for the future. Here's the temperature in 1950. We see that the temperature has gone up, about almost a degree. This is the kind of safe line that the United Nations has said, let's try to keep temperatures below 2 degrees C. But if we look at the projections for the future, and these are for different emission scenarios, this is kind of, the red one is business as usual, and then these are also kind of other scenarios. We see that we're going through this 2 degrees safe zone by 2050 in the middle of your life, actually. There is a possibility of an actual trajectory where we get the climate to stabilize. And this is what some people would really like to see. And in order to get there, we have to re-engineer our planet in some way, not in a dramatic way by putting mirrors in this sky, although you could imagine that, but by changing how we use energy, our fundamental relationship with energy, which fundamentally will affect almost every engineering field, and quite dramatically. So, but here's a challenge, and this is part of my second thing that I've learned. It's a little story. In 1850, we took fossil fuels that are in the ground and we burned them for energy, which was an amazing thing, which produced everything we have in our society. But we put 1,500 gigatons of carbon into the atmosphere. That's caused our planet to warm. If we want to keep our planet at this 2 degrees safe zone, where some people think if we get above 2 degrees, we're really going to kind of mess things up. If we can keep it at 2 degrees or lower, we'd probably be able to adapt to that. Then we can only burn another 500 gigatons. We can only put another 500 gigatons of carbon into the atmosphere. The challenge is that there's at least 3,000 gigatons of carbon in the ground. Oil, natural gas, coal. And we're clever, us engineers, we're clever at getting it out. Fracking and all those things are really interesting ways to get the remaining oil out of the ground. So at the current rate of burning, we only have 15 to 25 more years before we reach that level. So we're going to have to get busy. So, second thing that I learned is that we have to keep it in the ground. Keep it in the ground, meaning keep fossil fuels in the ground. We have to stop taking fossil fuels and burning them. Or we have to figure out a way to burn them and then grab the carbon and then throw it back into the ground. If we burn the 3,000 gigatons of carbon, we'll totally screw up our planet. When I mean screw up, doesn't mean that we wouldn't be able to live here, but it probably means we couldn't have 7 billion people living here as we do now, that we wouldn't have, a large amount of unrest. So here we get to the kind of fun part, because the reason I say it's fun is that you're going to be involved in this, especially as choosing the profession as an engineer. So how do we do this? How do we get on that kind of green track? How do we stabilize our climate system? Anybody know who this guy is? Right, Elon Musk. So maybe a little younger version of Elon Musk. But, this is, some people think, the most visionary CEO in Silicon Valley or in our country today. I would kind of agree with that. Even Donald Trump likes him. Because this guy is doing some, Donald Trump doesn't like many people in Silicon Valley. But this is one who anyhow, he's got Solar City, that's one of his companies. He's got Tesla's another company. They're doing batteries. In fact, Tesla's no longer an automobile company. It's an energy company. They just kind of changed over the last few weeks. So there's a reason for this. And it kind of leads me to a 3-step plan to reduce emissions. So 3 simple steps for how we can get on that trajectory to stabilize our climate. And this isn't Elon Musk's idea exactly, but a lot of us have thought along these lines. Step 1, reduce energy demand. So do everything you can to reduce the demand on energy. It'd be like conservation, turning off lights, making things more efficient. Pretty simple. Number 2, electrify everything. Electrify your cars, electrify heating, electrify cooling. You can think about your house, you could think about an industrial process. That would mean get rid of natural gas from every home. In fact, the Bay Area Air Quality Management District for the Bay Area by 2030 or 2040 would like to see natural gas gone. So you no longer stoves with natural gas, no longer heating. And then the last step in this is get your electricity from renewables. So it's a pretty simple kind of 3-step plan. But when you really think about it, is it practical? And if you were asked to design a plan using these ideas for the Bay Area, for California, for the whole country, that's a pretty challenging thing because we do not work in this way. We're kind of interested in reducing energy demand. We haven't been interested in electrifying everything, and we've only starting to get our electricity from renewables. So as a climate scientist, I studied climate models. I saw the predictions for the future, and I kind of got this. So I decided, I wonder if we could do this with an ordinary house. And this happens to be my house, or my wife Claire and I, we live here. So this is our home. So we tried to apply those principles, the three-step plan, to just a kind of ordinary house. So I'm going to show you what happened. So our first step was to reduce energy demand. So we had an opportunity to do a remodel. So we started with this stuff, thermal and sound control insulation. This is cellulose insulation. It's kind of like newspapers and old blue jeans. And we put it in as many places we could find. And we basically tried to insulate our home. So here's the contractors that came, and there they are in the attic blowing this stuff in. This is actually another type of insulation on the bottom of that's insulating the floor. You can't use the cellulose because of gravity, it would just fall to the ground. And then we put it in our walls as well. And so they drill holes in the wall, it's kind of a hassle. And then they just stick that stuff in there, and here it is. You can see the insulation. And then luckily for me, one day, my colleague, who's a fire weather specialist in meteorology, he had this FLIR, F-L-I-R, infrared camera. Cost $100,000, this camera. It's really cool. And it can, when I point it, because this is in the middle of the construction, you can start to see, you can see the holes. They haven't covered the holes yet. And you can get a thermal structure of like what's going on. And so I started pointing it, all kinds of looking at, oh yeah, wow, the insulation isn't working. Then I even pointed at this guy. That's our general contractor. Where do you think most of his heat is coming out of? I wouldn't go in there, right? But then one morning, I pointed it at this wall that was being hit by the sun. And they were halfway through. They hadn't finished the day before. And what I could see is that they had put insulation here. They drilled these holes up here. But there was a diagonal beam here. And this diagonal beam was preventing the cellulose from going down here. And I was like, oh my gosh, they're screwing up. But I never would have known without having this infrared camera. So I sent them the photos, and then they drilled some more holes and stuff like that. I was pretty happy. I was pretty proud of myself, actually. We also did stuff with our windows. So we got double pane windows, have argon inside them to help prevent heat loss. So we did everything we could to try to conserve energy. So we really well insulated the home. Second part is electrify everything. So we took our natural gas heater and we got rid of it, and we replaced it with a mini split heat pump. It's basically like a refrigerator. Takes the warm air from outside and pumps it into your inside. The MEs in here would know that pretty well. Actually is about 4 times as efficient as an electric resistance heater. Of course, those electric resistance heaters are not very efficient. They're kind of like a light bulb. But it is a pretty good way to heat your home using electricity. We also installed solar hot water, and this is a pretty simple system, just some pipes you put on your roof. It's a passive system, and there they are installing it on a roof. And then we put an electric flash hot water heater, because in the wintertime, if you're just getting your hot water from the roof, it's not going to be hot, especially early in the morning. So this just bumps the heat up to whatever temperature you want, and that system seems to work pretty well. So we electrified things, and then get your electricity from renewables. So we put sun power solar panels on our roof with microinverters. If you know about solar, you know about microinverters. And so there's the solar guys. Why is it that solar installers never wear shirts? It's like kind of the classic thing, you know, in solar installation. Anyhow, there they are putting our solar panels on the roof, and then this is our whole system. So that's solar electricity, and this is solar hot water. We actually even installed another thing, which is a solar air heater, which is just a box that heats up in the wintertime and just pumps air into our room. And here's the system. And with these microinverters, it means there's an inverter on every solar panel. And so you can identify the energy for every single solar panel. So if there's shading, that's not an issue. This is a little experiment I was doing with whether I should clean my solar panels and what the efficiency would be like. So what are the results of because I know you guys like data and numbers, what are the results of our install or our energy 3-step plan? Well, here's the kilowatt hours. This is the amount of energy we've used per day for the first year, a couple of years living in the home before we did the energy conservation work. So we were averaging about somewhere around 30 kilowatt hours Most of it coming in the wintertime. So almost all of it coming in the winter. In the summertime, we weren't using that much energy. And then after we did the remodel, we could see that our energy use went down a lot. Now this has nothing to do with solar panels, it's just the energy used. So that's that first step, reduce demand. So we were able to cut our demand by like three times. And I'll tell you that our home is much more comfortable. It's not as drafty, it's more soundproof, it's a nicer home to live in. So it's not a sacrifice. We have not sacrificed anything. In fact, we've become more comfortable. And if you do a running mean, and so I geek out on the Excel stuff, and I want to know, okay, how's the energy use change? So you can kind of identify before and then after. Now, we also had electricity being generated by solar. So this is for the last 6 years. And so you can see our solar produces more energy in the summer and less in the winter. So if we go back to this and we put how much energy we generate with solar, we can see that we're producing more energy than we're using. So we're actually starting to make a difference here. In fact, we're producing almost 3 times the amount as energy than we're actually using. So we've overproduced. So I was thinking, oh great, we're overproducing. Maybe we could get an electric car. And then you could use that electric car, that energy from the electric car. Now I'm a professor, I can't afford Tesla. So maybe a used Nissan Leaf or something like that. So what we learned, at least from a kind of a personal standpoint, was that it could be done. That we could reduce our energy use significantly. We could produce that from renewables. And maybe it could even power some of our transportation. So what about doing that at scale? That's kind of the plan of what states like California, Governor Brown is kind of completely in line with this kind of idea. And countries are looking towards. Now, at a more personal level, in 2008, I co-authored a book with a chef about food and climate change. And this has kind of led me into directions I hadn't anticipated. But it made me think about my own life, not just my home, but other things in my life. And so like 2 things about me that I enjoy are bicycles and burritos, especially burritos. And in fact, in doing research for this book, I was studying the food system in some detail, and I started to study burritos in particular. Just because I like burritos, I might as well study them, try to understand something about them. In fact, I created something called the Burrito Enjoyment Index, and I looked at the average American, and I compared it with myself. And indeed, I am off the charts in comparison. But this burrito thing led me to start to look at the energy required to make burritos and what the kind of carbon footprint was. So I did a burrito showdown, comparing a chicken burrito with a beef burrito, looking at the carbon footprint or the carbon emissions to grow and manufacture and to do everything it's required. And I was kind of shocked to find that the carbon footprint of a beef burrito was like 5 times higher than the carbon footprint of a chicken burrito. And when I go to Chipotle, there's no price difference there. There's like chicken, beef, whatever, or La Vic, which is where I'd recommend that you go. And when you go there, get the orange and the green sauce. Putting them together, I've been a professor here for 14 years, having orange and green sauce on my burritos. I'll just tell you, that's the way. But the choice of your burrito actually could potentially have a large impact on our climate system. So I didn't know that before I started doing this research. I did know that if you had a car like a SUV, it only gets 12 miles per gallon, there's a lot of carbon emissions. Compare that to the Prius, okay, of course you're making an impact. But your diet can have a similar impact as the type of car you drive. That's one of the things we learned in researching this book. Now the other thing that I like is bicycling. And so if I was going to compare driving with bicycling, what's the carbon footprint of riding your bicycle? 0. No, that's not right. Why isn't that right? Yes?
Based on the energy, or based on the food you eat, really.
Thank you. Yeah, like where do I get my energy? Burritos, now you're talking, right? So it turns out it depends on the flavor of burrito you eat. Right? Because one burrito is going to have a high carbon footprint, the other is going to have a low. So the average equivalent fuel economy for a car versus a bicycle. For a bicycle, it's 75 miles per gallon all the way up to 500, depending on your burrito, right? So this one is a beef burrito, 75 miles per gallon, all the way up to a chicken or veggie burrito, 500 miles per gallon. So I learned some interesting things in writing this book. Now, I gave this kind of talk about burritos and silliness like that to many, many folks in the year 2008. But there's one group of people that was missing from the bookstores that we go to, or libraries, or university talks. And those were young people. And as Josh said, this kind of led me to do some very different kind of work, still kind of silly, but related to creating educational materials for kids. And we decided kind of strategically to work with kids because we know kids can have an influence on their parents. So this Lazaniak and Pollan paper reported that children average a purchase influence attempt every 2 minutes when shopping with their parents. You can kind of imagine a kid like pulling on their dad like, I want that thing. And we also know that kids can have an impact on their environment. Young kids can get involved in projects, but these kids later become activists, and these activists may even become engineers who work on projects for a common good. And I would say that most engineers in this room want to do something that they feel good about. You know, most of us, you know, I used to work in the defense industry at Hughes Aircraft. You know, it wasn't the greatest. It's nice to work on things that are going to make the planet a little bit better, people's lives, the environment. And so we think that working with kids can make a difference. So we started this about 5 years ago. Scientists and artists and educators and engineers here at San Jose State. We created, we had funding from NASA, and we have current funding from National Science Foundation. And so we created Green Ninja films, animated live-action films. We have some games and some other programs. And our Green Ninja show, which if you just Google Green Ninja, you can watch some of our videos. They're kind of silly. They also include episodes with Dr. Burrito. And here I am interrogating 2 burritos with my burrito meter that's hooked up to my phone. And and here, are you ready for a photo you've never ever seen or even imagined? Most of you have been to Chipotle sometime in your life. Well, have you ever seen a Chipotle farm? This is where the burritos grow. This is where they come from. And look at the roots on this one I just pulled out of the ground. Isn't that great? So, but our goal really is actually more serious. We want to use formal education to actually produce verifiable reductions in carbon emissions. So we want to use fun and engagement and engineering and science, but actually we want to measure and demonstrate that our flavor of education can actually reduce emissions. And that's our goal. And right now we have about 200 schools who use Green Ninja materials, primarily in the Bay Area. But there's new science standards that are national, and our goal is to get Green Ninja materials across the country. And we think that a kid who does Green Ninja stuff for 1 or 2 years, their families, like their life, will change in some way that will actually have an environmental impact. So the third thing I've learned is about dreaming big. So we actually want to see this across our country. The last thing I'm just going to mention to you is kind of the path forward. I'm going to read to you an excerpt from a letter that was sent to the U.S. government. This is a letter to U.S. policymakers from all these organizations. These are some of the top scientific organizations in the country. AAAS being the kind of the one that publishes Nature, Science magazine. And the American Geophysical Union, the American Meteorological Society, they all co-signed on this letter. And it said, observations throughout the world make it clear that climate change is occurring, and rigorous scientific research concludes that the greenhouse gases emitted by human activities are the primary driver. Climate change is happening, humans are responsible. All these groups agree. This was sent in last year, in 2016, sent to President Obama. And so Obama, here he is at the Paris Climate Agreement. But I would say that in in truth, Obama was there 8 years and president. His first 4 years in terms of climate change, he didn't do much. He did one piece of policy that was to put some type of regulations on automobile fuel efficiency. But from the climate standpoint, not much really happened. In his second term, things got a little bit better, and especially towards the end, he decided, for whatever reason, that climate change was really going to be his thing. And he was going to try to do as much as possible. So I'd say his last 2 years, he did almost everything he possibly could. And his biggest achievements, fuel efficiency for trucks, this was a big one, US and China reached historic climate change deal. So the US and China made an agreement. That was always the big sticking point in terms of actually doing anything internationally to cut emissions. And then we had this climate accord, the Paris Agreement, which is an international agreement ratified or signed by the number of countries required that says we're going to actually do something about climate change. It's not binding, but it's a good first step. And in fact, I would say for like 1 or 2 months, I actually felt like, oh my gosh, the United States is kind of like a leader in terms of doing something about climate change. And then that changed. And with every government change, there's going to be a change. This one is more dramatic, at least from my standpoint. So Donald Trump says, I'm not a big believer in global warming. And that's not just a recent thing. So I'm going to show you some of his tweets. The very expensive global warming bullshit has got to stop. Our planet's freezing, record low temperatures, and our global warming scientists are stuck in ice. I guess that's me, right? The concept of global warming was created by and for Chinese in order to make US manufacturing non-competitive. And we should be focused on clean and beautiful air, not expensive business clothes and global warming. A total hoax. So you can see why someone like myself, as a climate scientist, would be, this would be a big transition, a big change for us. He has taken the steps that we thought he would. These are 3 of his appointments. Scott Pruitt, just a week ago, head of the EPA. He's sued the EPA so many times. He's said we really should get rid of the EPA, the Environmental Protection Agency. Rex Tillerson, former CEO of ExxonMobil, the fossil fuel company that put the most money into climate denial and climate skepticism, is now as our Secretary of State. Rick Perry, Department of Energy, famously quoted in a debate about the 5 public agencies he was going to get rid of. He couldn't remember the Department of Energy as that one. It's kind of classic. Now he's the head of the Department of Energy. So it doesn't look good from a climate change standpoint. But having said that, our hope is that some of these people, that some of that was rhetoric. And for example, Rex Tillerson also supports a carbon tax. And many businesses actually do. And a carbon tax would mean a price on emitting carbon. And actually, Elon Musk supported Rex Tillerson to be Secretary of State. And a lot of environmentalists said, Elon, what are you doing? And he said, I think this is our chance to get a carbon tax, which would actually, most environmentalists and most people that are interested in climate change are in support of some type of carbon tax. Rick Perry, first things he said was, we can still, produce energy and still support renewables, but as well use fossil fuels. So that's kind of a mixed message. I will say though that in the climate science community, we are quite concerned. And it's not just in the climate science community. In fact, the science community in general. And so this is a challenging issue. There's a March for Science. So we had the Women's March that happened a few weeks ago. There's a March for Science on Earth Day. And the reason other scientists are concerned is that there's this we're starting to tread in this what is real and what isn't. This idea that are facts really driven by data or are they just opinion? Can you just say things and that happen? If you just will it, will that mean that the number of people at the inauguration just is like that? And so that's why the scientific community has kind of gotten around this idea. And they said, on April 22nd, we're going to walk out of the lab and into the streets because we want to make sure that we value science and engineering. And to kind of put this in your perspective, what if all of a sudden someone said, oh, you know, that engineering flavor you're doing, it's kind of hoaxy, it's kind of bogus, you know, it's not really true. And that's what they've done with this particular flavor of science. And so I probably won't go to that march, but I probably will go to the People's Climate March because it's a group that this isn't just really about science, this is about people. And it's about people of color, it's about indigenous folks, it's about healthcare. And so there is a growing group of people who care about this issue. And this is the point for me, is to be strong. And it's not just for me, but for all of us, that the things that are our government, some elements of our government, have always been challenging. Today's government might be more challenging for many of us, and that we have to be strong, that we have to try to preserve our democracy, we have to, you know, get involved, and at least that's how I'm taking it at a personal level. I'm going to share, the last thing I'm going to share with you, the National Society of Professional Engineers, the Code of Ethics. This is, if you become a professional engineer in your field, or even if you don't, this is the Code of Ethics for engineers. And there's these fundamental canons, and I'm going to share with them 3 of them with you, because I think they're particularly relevant to today. Number 1 says, hold paramount the safety, health, and welfare of the public. So, in the engineering work you do, you want to think about the public. I mean, you're working to create a public good. And if there's something you can do in your engineering that conserves energy, then you know you're doing something about climate change. If you can reduce a milliwatt in that semiconductor, you're going to make the battery last longer, you're going to reduce the amount of electricity being used. If you can use different materials in a civil engineering project for a bridge, you know you're reducing energy. If you can write code that doesn't get the fan to turn on as much because it's more efficient code, you're going to reduce energy. Perform services only in the areas of your competence. That's kind of a no-brainer. But issue public statements only in an objective and truthful manner. So this has been, and this is why the scientists are getting a little alarmed right now, is that, you know, we do base our engineering and science on, you know, Newton's second law, on how mathematics works, on some very fundamental principles. And that's part of our code of ethics, is to be objective and truthful. And that's what we tried to do in science all along. So good luck with your engineering. This field and this topic will kind of interact with you in ways, and I hope that this has given you some background. Thank you very much.
Thank you.
We have time.